A 20-kilogram child climbs 3 meters up a ladder to the top of a slide, which is perfectly straight and makes an angle of 37 degrees with the ground. The coefficient of kinetic friction between the child and the slide is 0.25. She starts from rest at the top of the slide. So in part A, we want to describe the complete energy cycle for the process from the bottom of the ladder to the bottom of the slide. So she starts out with chemical energy in her muscles, which she's using to allow her to do work to climb the ladder with both kinetic energy and gravitational energy when she reaches the top of the ladder. And then as she slides down the slide, she's turning her gravitational energy from having height into kinetic energy, while at the same time, because of friction, she's losing some thermal energy to the slide until she reaches the bottom of the slide where she has just kinetic energy left, and she has caused the slide to pick up some thermal energy from the friction. In part B, to calculate the work done by friction on the child as she slides down the slide. So she is sliding down the slide, and the frictional force is directed up the slide in the opposite direction. So we could just say that the work due to the non-conservative force of friction is equal to, since the force and displacement are in opposite directions, we say negative force of friction times the displacement. Now we've got to figure out what both of these things are equal to, both the frictional force and the displacement. So if you look at the shape of the slide, which makes this triangle, a right triangle, where this angle over here is 37 degrees, to solve for the distance down the slide, this d right here, since we know the opposite side of the slide is 3 meters, we can use one of the trig functions. We know the opposite side of the triangle. We want to know the hypotenuse, so the trig function with the opposite and the hypotenuse in it is sine. So we could say the sine of 37 degrees is equal to the opposite side, which is 3 meters, over the hypotenuse, which is d. And when you rearrange this equation for d, you'll get 3 over the sine of 37, which comes pretty close to equaling 5 meters. So we'll just round it to 5 meters. Okay, now we got to get the frictional force. So for this one, it helps to draw a free body diagram for the child as she's sliding down the slide. So she has the gravitational force acting on her. She's got the normal force perpendicular to the slide, and she's got the frictional force directed up the slide. And the frictional force, if we look at this free body diagram and assume that she is accelerating in the direction down the slide, if we assume this is her acceleration, the frictional force, we cannot assume the forces in that direction are balanced. But what we can say is that we know the frictional force is equal to mu k times the normal force. And if we take this free body diagram and break that gravitational force into components, in other words, if we rotate the axes so they're lined up with, that's your x direction and this is your y direction, if we break that gravitational force into components, what you end up with will look like this. You've got the normal force, the frictional force, this component of gravity is Fg sine theta, and this component of gravity is Fg cosine theta. So in this direction, the one that I'm circling, the forces are balanced because the child is not accelerating perpendicular to the slide. So we can say that the normal force in this equation is equal to Fg cosine theta, which is just m times g times cosine theta. So the frictional force, the full equation for the frictional force, is mu k times mg cosine of theta. And if we take that whole equation and plug it in for that frictional force right there, we find that the work due to the non-conservative force of friction is equal to negative UK mg cosine of theta times d. And if you plug all those numbers in and make sure your calculator is set into degree mode, you should get an answer of about negative 200 joules. Okay, let's use the work energy theorem to calculate the speed of the child at the bottom of the slide. Now, if the slide were frictionless, then we could just use conservation of energy. But friction is the only non-conservative force that's doing work on her, so we can't use conservation of energy. We're going to use the work energy theorem, E initial plus the work due to non-conservative forces, which we've just calculated, will be equal to the final energy. And then we can replace the EI and the EF with KI plus UI and with KF plus UF. And let's see which of these terms goes to 0. She starts from rest at the top of the slide, so the initial kinetic energy is 0. She does have height at the beginning, so this would not be 0. We know this isn't 0 because we just calculated it. At the bottom of the slide, she is moving, so this is not 0, but she no longer has height at the bottom of the slide, so that last term would be 0. And if we plug the formulas in, we'll get mgh initial plus the WNC is equal to 1/2 mv squared final. And if we want to solve this whole thing for v final, I'll just take this side of the equation and multiply it by 2, since we're multiplying both sides by 2 to get rid of the 1/2. Divide everything by m to cancel that out, and then to cancel the squared out, we'll just take the square root of the whole thing. So in your calculator, you're just going to put in all this stuff. Remember, m is the 20, g is 10, the height initial is the 3 meters, the WNC is negative 200, and then the m is 20. And if all that is put correctly into the calculator, you should get that answer of the 6.3 meters per second. Part D, explain why the speed of the bottom of the slide would be the same regardless of the child's mass. This one just takes into account, well, this one just really wants you to notice that if you look at this work energy equation, when we cancel out these terms, that first term, the U initial, had mass in it. That final kinetic energy had mass in it. But what about this WNC? We couldn't cancel out mass because 2 of the terms had mass in it, but this one did not have mass in it. But if you look back at the formula that we used, the formula actually does have mass in it, and we use that mass to be able to calculate this. So if we'd have taken this whole formula right here and plugged that formula into the WNC instead of just putting in the negative 200, then we could have canceled out the mass in each of these 3 terms, and that would have made it irrelevant to the problem. And you still would have ended up with the same answer of 6.3 meters per second. And finally, part E, describe the circumstances for which the child would slide down the slide with a constant speed. The first thing is, if she starts from rest, it's impossible for her to have a constant speed because she has to accelerate. So the first thing is, instead of starting from rest, she is going to have to kind of push off at the beginning to give herself some kind of initial velocity. But then what it's saying is that velocity has to stay the same the whole way down the slide. So her kinetic energy would not be increasing, even though her gravitational energy would be decreasing because she's getting further down the slide. And the only way that's possible is if you look back at this equation, and I'll go ahead and rewrite it, the E initial plus the work due to non-conservative forces is equal to the E final, and when you plug in Ki plus Ui plus WNC is equal to Kf plus Uf, the way to think about this is that we said that the final potential energy, the final gravitational energy, is 0 because she's at the bottom of the slide. Now, we said in this case she's going to have to give herself a push off to get started. So her initial kinetic energy would not be 0 this time, but we did say that she's moving at a constant speed, so her initial kinetic energy and her final kinetic energy would be the same. So we could actually just subtract that from both sides of the equation to get rid of it. So I'll just cross it off. Remember, we're saying it's not going to go to 0, though. And what that shows you now, with what's left, is U initial plus WNC equals, well, there's nothing left over here, so it's 0. So U initial plus WNC equals 0. And since the WNC is a negative amount, because it's the work done by friction, what that means is that the work done by non-conservative forces would have to be a large enough negative number that it completely wipes out the initial gravitational energy. So in other words, all of her initial gravitational energy is lost due to the frictional force.